Good morning, dear students. In the yesterday's class, we discussed about the accuracy and precision with these two examples. So now we have to discuss the remaining characteristics of static characteristics. So what are those? The second one here is the static error. It is the algebraic difference between the indicated value of the measuring system to the true value. So that means if the measuring system can able to identify a certain value, that can be called as indicated value. So if the measuring system actually it is need to identify a certain value, that is can be called as true value. If the measuring system identify value and the true value difference can be called as static error. So the static error can be defined as static error is equal to indicated value minus true value. So when the static error is positive, it is positive when the indicated value is more when comparing to the true value. Then what is the third one? Third one is correction. It is the algebraic difference between the true value to the indicated value of the measuring system. So see the difference between the static error and the correction. So error is the difference between indicated to true value, but the correction is difference between true value to indicated value. So the static error is exactly equal with the minus of correction error. So how we can able to calculate the correction? So correction is equal to true value minus indicated value. So this is also equals with minus static error. So next one is uncertainty. It is the expressive of ranges of variation of the indicated value to the true value, and it indicates the probable limits of the error due to the disturbing inputs. So let us take a voltmeter. So if you are giving some voltage for that, so it needs to provide that voltage as an output. So even the input is not changing, sometimes the output can vary. So which can be called as uncertainty. Without changing any input, if sometimes the output may vary, so can be called as uncertainty. The range. So it may be, suppose if you give some 5 volts to the voltmeter, so it has to show 5 volts. So sometimes it may be after some time, that means after 2 minutes or 3 minutes, it was showing that as a 5.1. After 3 minutes, it was showing that as a 4.9. So likewise, this 0.1 difference can be called as uncertainty for a certain time of range. So the next one is repeatability. So for the repeatability, we need to consider several points. So let us take the group of outputs. So group of outputs means, so for a single input, so there will be several conditions. Before going to this, let us see those conditions. Same observer. So here observer is same input, same method, same environmental conditions, and with a short span of time. That means we are not taking more time by using that instrument. So here the conditions is same observer, same input, same method, same environmental conditions for a short span of time. So for the group of outputs, that means the outputs is taking many times by the same observer, same input, with the same method, by the same environmental conditions for a short span of time. So even in these situations, if the instrument is showing the same result, then it will have more repeatability. So what are the things? If you take the group of outputs with the same observer, with the same input, by the same method, by the same environmental conditions, with short span of time, if the instrument is giving the same output, then it will have more repeatability. So repeatability means it reflects the closeness of the agreement of the group of output signals obtained by the same observer for the same input quantity using the same method under the same operating environmental conditions over a short span of time. So this is the repeatability, one of the characteristics in static. The next one, reproducibility. So now for the same conditions, we have to consider the same 5 conditions, but here in this case, so group of outputs, we are taking number of outputs, but here the case is different observers, different inputs, different methods, and different environmental conditions, and different at different times. So if the instrument is collecting, now we are collecting more outputs from the instrument with the different observers, with the different inputs and different methods, different environmental conditions in different times. Even in these conditions also, if the same result it was giving, accurate result it was giving, then the system will have more reproducibility. So what is meant by reproducibility? Reproducibility, it reflects the closeness of argument of group of output signals obtained by the different observers for the different input quantities using the different methods under the different operating environment conditions over a different span of times, otherwise over a prolonged period of time. So next one is stability. It defines the ability of the measuring system to maintain its standard of performance over a prolonged period of time. So very near what to the uncertainty. So uncertainty means if there is any change, that can be called as uncertainty. If there is no change, it can have more stability. So what the difference? Uncertainty means if there is any change, if you place the same input for the long time, that can be called as uncertainty. Stability means if it was not changing for a long periods of time, then the instrument will have more stability. So next one, 8, zero stability. It defines the ability of the measuring system to restore to zero reading after the input quantity has been brought to zero. So let us take a voltmeter. So if you measure some voltage here, let us take it was 5 volts. So after removing that terminals from your voltmeter, it has to show 0. It has to show 0. That can be called as zero stability. So how much fast it was going to 0, that much of zero stability that instrument had. Sometimes you can take this digital instrument and analog instrument. So if you remove the voltage from a digital instrument, automatically it will become 0 in a fast manner. So let us take the analog instrument. If you measure a voltage from that, it might be take long time when comparing to digital signal. So that means the digital one will have more zero stability when comparing to the analog one. Sometimes few analog meters will struck at 1 or 0.5, 0.2. So this is also will come under zero stability. So now I got the difference between the stability and zero stability and uncertainty. So uncertainty means if the measuring system was measured a input for a long time, if it was showing some disturbances, it can be called as uncertainty. So if the measuring system is maintaining the same output, if the input was not changed for a prolonged periods of time, it can be called as stability. If the input is removed from the measurement system, if it was showing the 0 as much fast as it can be called as zero stability. So next one is resolution. So it is the smallest increment of input quantity to which the system responses. That means, so similar like the megapixels of a camera. If the megapixels is very high, it can able to show the in detail of a photo. So here, if the resolution is more, the instrument can able to identify a very small change in the measurement. So if the small change can able to identify by a measurement system, it will have more resolution. So it is the smallest increment of input to which the system responds. So next one, sensitivity. It defined as the ratio of the change in output signal to the change in input quantity. So sensitivity, there are few types of sensitivities you can see later. So it is the ratio between the change in output to signal to change in input quantity. If you changing the input, the variation in the output is linear, then the sensitivity is linear. If it is curved shape, then it can be called as incremental sensitivity. So how the incremental sensitivity will be there, how the linear sensitivity will be there, you can see here. So let us take this one is incremental sensitivity. That means if the ratio of the input signal to the output signal is not always same. So up to certain range it was one ratio, up to certain range it was another ratio, and there are several ranges here, you can see here. And see this is one range. Here in this range the graph is almost linear. So that means in this range it will have certain ratio. So the ratio is different. And you can see here in this range it has another ratio. In this range it has another ratio. And in this range it is also have another ratio. Let us take a voltmeter which will have certain placements. Let us like 0 to 20, thereafter 200, thereafter 600, and thereafter 1000. 20, 200, 600 and 1000. That means if you can able to give the voltage in between 0 to 20, you have to place the knob in between 0 to 20. Otherwise it cannot show. That means the ratio at the input change to output change is different at 0 to 20. So, and they are similar like 200, 400, 600 and 1000. So that means even it was non-linear characteristics, we have to consider few linear characteristics as based on the curve. So it was, in the first case you can see here, so up to this the curve is almost linear, not perfectly linear but of course almost linear. So this is 0 to 20 range. So in this range it can able to identify 0 to 20. So here the 20 is just for example. So the next one, so let us take it was 20 to 200. If the voltage, if you think the voltage is 20 to 200, you have to place the voltage knob at 200. So let us assume this is the range here. So here in this case from 20 to 200 it was somewhat linear, not perfectly linear, somewhat linear. So we have to calibrate the instrument again as per our results by using absolute standards. So this is another range. So let us assume it was 200 to 600. So it is also not completely perfect straight line but almost perfect. So here also another range. So we have to cut that curve into different ranges so that we have to make that as some linear properties up to certain ranges. So this can be called as incremental sensitivity. And one more thing is there, so which can be called as linear sensitivity. So here from the 0 scale to full scale it was completely linear. 0 scale to full scale it was completely linear. So this type of instruments will have no problems, but this type of instruments are very rare, of course practically impossible. So more instruments will have incremental sensitivity. Linear sensitivity means it is ideal case, it is not possible in the practical cases. So next one is responsiveness. It denotes the smallest change in the quantity under measurement. It denotes the smallest change in the quantity which is under measurement. If the system is responding even for the smallest change, that can be called as responsiveness. Even the system is responding for the smallest changes, that can be called as responsiveness. So next one, linearity. It defines the proportionality between input quantity and the output quantity. Sensitivity is constant for all values. So here, that means if the sensitivity constant for the 0 to full scale, then it will show a line, can be called as linear. Previously we checked it. So here, so in the linear case means the sensitivity is constant. If the output to the input ratio is constant up to the long periods of time, then the such system will have more linearity. You know that this is the linear case, and which can be called as linear characteristics, you know very well. And this one is non-linear case, so which will have non-linear characteristics. So in this case we have to divide into certain parts, but it is actually happens, the linear case will not happens practically. So the yellow line indicates the linear characteristics and the red line indicates the non-linear characteristics. The linearity means if the system sensitivity is constant up to the 0 scale to full scale, then it can be called as linear. So next one is drift. It is slow variation in the output of the measuring system which is not due to any change in the input quantity. See here. So it is almost nearest term to the uncertainty. Even we are not changing the input, the needle is changing. That can be called as uncertainty. So here it is a slow variation in the output of this measuring system which is not due to any change in the input quantity. But we are not changing input quantity here. Maybe some disturbances. Due to some disturbances it can able to change sometimes. So such thing can be called as drift. So next one is threshold. It defined as the minimum input quantity that is necessary to cause a detectable change in output signal from the zero indication. So what is meant by threshold means, so let us take an analog meter which will be best example for this. So let us give some voltage, very small voltage, it might not respond. Even that means the indicator will not move from 0. So by improving the voltage it may have move at certain voltage. That range can be called as threshold. That means it must have to respond for the minimum input quantity. So the input quantity required for that is can be called as threshold. So next one is deadband. It is defined as the largest change in the input quantity to which the measuring system does not respond. It happens due to static friction or hysteresis. So threshold means it has to take some time. So that means that can be called as threshold. So it will take some time. So that zone can be called as deadband or dead zone. So it happens because of hysteresis. For which one it can happen? It will happen due to hysteresis. So what is meant by hysteresis? This is the graph one we can consider here. So if you can take a voltmeter, let us give some voltage, increasing voltage. So it will start from 0. So up to certain full scale value. So it will reach us to maximum. Thereafter, if you can able to reduce it, the voltmeter now it was without calibration. So by reducing the voltage, it may reduce the voltage, but it will not adjust it 0 sometimes. Not sometimes. If it was not calibrated 100%, it won't adjust the 0. So thereafter, if you can give the negative values, again it won't adjust the zeros and it will goes down. Thereafter, if you can increase the negative values, again it will goes to the full scale value certain by certain curve. This curve you already know that this can be called as BH curve or hysteresis curve. So it won't adjust the starting point again. So this type of errors can be called as hysteresis errors. So practically after calibration, these type of errors will be occurred. So in instruments. So that is in BH curve. This was in instruments or measuring systems. So what it meant by dead zone. So see here, this will happen in instruments. So first it was started from 0, but it was not starting responded for 0. After some time it was responded. Thereafter it was reached to maximum value. Thereafter come back and negative values, and thereafter negative maximum value, and thereafter it was reaches to full scale maximum value. So, but starting time, it was taken some time to respond, can be called as dead zone. So, the response difference can be called as threshold. The zone in that place can be called as dead zone. So, next time, dead time. So, time, the time taken to respond, the instrument can be called as dead time. So, that means that dead zone time can be called as simply dead time. So, here, so for the positive values from 0 to certain time it was taken, that time, so that zone can be called as dead zone. The time period can be called as dead time. So here in this case, another case, so it is for step input and that was for ramp input. So the ramp input is not responded from 0. So it was responded after some time. Thereafter it was linear. So that zone can be called as dead zone and the time required for that can be called as dead time. So next static characteristics, span and range. So these two terms can be represents the lower and upper limits of the measuring system. If set in a voltmeter can able to calculate for 0 to 700 volts, then the lower limit is 0 and the upper limit is 700. So that means these limits can able to tell by using the span and range of the system. So what is meant by span and what is meant by range? So span, it is the difference between the full scale and the lower scale of value of the measuring system. So let us take a voltmeter is reading from 0 to 100, then what will be the same 100 minus 0, which is 100 minus 0 is equal to 100. This can be called as span. So range, what meant by range? It indicates the full scale to lower scale values of the measuring system. So what will be the difference by seeing these two? So it is the difference it indicates. So difference means 100 minus 0, 100. So it is a value. But range means 0 to 100. You have to tell like that. What is the range of this instrument? 0 to 100. What is the span of this instrument? 100 minus 0, which is equals to 100. So 100 is the span, 0 to 100 is range. So here, and best example for that, let's take two voltmeters. One is the range of 0 to 100 and the other one is 100 to 200. So what is the span now? So in both cases span is same. So that means 100 minus 0, which is equal to 100, and 200 minus 100, which is equals to 100. So in both cases span is same. So but what about this range? So range in the first case is 0 to 100 and the second case is 100 to 200. So this is the major difference between the span and range. So we have to consider the span and range, all these are this type of static characteristics before selecting a transducer for a particular instrument. Then only that instrument can able to show the output in a accurate and precise way. So next one is live zero. The term applied to a measuring system whose output signal is not zero for zero input quantity. The term applied to a measuring system whose output signal is not zero for zero input quantity. Let us take few instruments which are not calibrated. It won't show zero. So that means it will fall down from 0 to some value. So most instruments are the analog instruments. So the indicator will not be at 0 if the voltage is if the input is 0. It might be down when comparing to the 0. So there will be one knob there, so that can hold the indicator. That will be under 0. So that means it will not be 0. The term applied to the measuring system whose output signal is 0, not 0 for zero input quantity can be called as live zero. So actually that is the live zero of it. It can respond for a certain input. Thereafter only it will shows from 0. Mostly it will happen in analog instruments. The 0 to 100 is, let us take some 0 to 100 is the voltmeter range, but initially the indicator will stay at down to 0. There will be some knob which can hold the indicator. So this can be called as a live 0. So that means without any input quantity it will shows not 0. So it can be called as live 0. That's why you can place that knob over there which can hold the indicator. So next one is scale readability. The term denotes the extent to which the reader is enabled to read the indications. So the term denotes the extent to which the reader is enabled to read the indications. So what is the meaning of this sentence? So scale readability means, so let us take an analog instrument and take a digital instrument. The user can able to observe more digits in digital instrument. Why? Because it can able to show more digits. If it have the 4 digits accuracy, it can able to show more digits. That means up to that extent the user can able to identify the accuracy. But in the analog it is not possible. Just we can able to say by seeing if the needle is available in between 2 values, we can place 0.5. Otherwise, if it is available 75%, then we can place 0.75. We don't know whether it was 0.75 or 0.7 or 0.8, but it is not accurate. But in the case of digital voltmeter, it is possible up to some extent. So that means the term denotes the extent. So if it have more extent to read the scale, then those scale will have more readability. That means digital instruments will have more readability when comparing to analog instruments. So then next one is input, the last one of the characteristic, input and output impedances. The impedance across the input terminals by removing the load is called as input impedance. The input impedance can be called as the impedance across the input terminals by removing the load. So let us remove the load from an electrical circuit and also remove the source and collect the resistance at the source side. Such impedance can be called as input impedance. What we have to do? We have to remove the load as well as we have to remove the source, and we have to connect the resistive meter, otherwise impedance meter, at the source side. If you can able to calculate the impedance at the source side by removing the source as well as load, that can be called as input impedance. So what will be the output impedance? So now in the previous case we removed the source as well as output, but here in this case we have to make zero source. That means zero source means voltage, for voltage source we have to make short circuit, for current source we have to make open circuit. So that is the making of zero source. So that means you need to collect the impedance at the output terminals by removing the output and by making the source as zero. So source as zero means voltmeter, voltage source means short circuit, current source means open circuit. So by these conditions you can able to calculate the impedance across the output. So such impedance can be called as output impedance. So we need to consider all these characteristics while considering the static characteristics of an instrument. So these will be useful while static calibration, and these will be useful while collecting the transducer for a particular measurement of a particular instrument. So these are the static characteristics, and these are 19. So next one is dynamic characteristics. So the dynamic characteristics of measuring system relate to its performance when the measurand is function of time. So what is meant by measurand here? So measurand is the quantity which is to be measured. So if the quantity is function of time, then the characteristics of measuring system can be called as dynamic characteristics. So the dynamic characteristic of measuring system relate to its performance when the measurand is function of time. So these are the several inputs you know. So these are the function of time. So we know that very well about these three step input. So here the output is constant from 0 to infinite time, and here it was ramp input. So these are the inputs which will have the function of time. So that means while using these type of inputs, we have to consider the dynamic characteristics. So here the ramp input. So the ratio between the output and input will be same if it goes through the origin. So this is the sinusoidal input, and this is different function. This is also the timer function. So these three types of inputs we can consider for the measurements. So step input, ramp input, and sinusoidal inputs. So this is about today's class. So in the later classes we can see the different terms available in dynamic characteristics. Thank you, dear students.